Let's talk a little bit about the cherry tree data. Okay, the main thing that we have is that we have diameter, height, and volume. Those are the raw measurements. And what we'd like to do is look at this idea of the dependency between volume and diameter and height, and we'd like to get the best model we can. Now, what I've done in the data file is I've added things like diameter squared, I've added diameter times height. Now, you could do that yourself, but I did it for you, so it's just there. And I also have diameter squared times height. Now, what's going on with all that? Well, okay, again, the raw data are diameter, height, and volume. And so what we could do is we could use linear regression on, volume is equal to some slope 1 times diameter plus another slope times height plus our intercept alpha. And we could look at those, and we could look at our dependencies and look at how good the model is and determine what that relationship is by looking at our adjusted R squared and at our various p-values for this slope and that slope. Okay, but knowing something about geometry and so forth, well, what I know is that if I'm looking at some tree here, there's my tree, especially a tree in a forest, it doesn't look so much like that. If you go into a forest and look at a tree, pretty much they just look like that. They tend to be very tall, and they don't have a whole lot of branches sticking out. And so I would say they look a lot like a cylinder. And so I might guess, actually, that given that the volume of a cylinder is, well, I'll put cylinder here, is equal to pi r squared, that's the surface area of the top or bottom, times the height, h. And, so given that, well, since radius is just half the diameter, I might expect the volume of a tree to simply be some, and I'll just call it a beta, times diameter squared h. Now, it's not going to be pi, because if it was a perfect cylinder, it wouldn't be pi, because I'm using diameter and not radius. But nonetheless, it'd just be some constant, and there wouldn't even be an intercept, a y-intercept. This would just be, I could think of that as my variable, which is what I did in the data above, and so there might be really good reasons for that. Now, most likely, if I ran this, if I really want to look at dependencies and so forth, and given I'm talking about trees and not cylinders, I may have a very good reason to believe that, well, yeah, it'd be some beta diameter squared times h, but then plus some intercept, because trees are trees, they're not cylinders, and so why not have some sort of intercept explanation. But again, oops, left off an E on volume. But again, I don't know that a tree should really do that because, again, what trees am I talking about? Well, I just have a data set here. I don't know if these trees looked like forest trees or if they looked like a tree out in my front yard. And those, again, are very different looking trees. And so I might want to explore what I think might be the best model. And so it's possible that I could get, going back to the, I'll just use a V for volume and D for diameter and H for height. It may very well be that this, if these are trees out in my front yard or something, plus alpha, this might actually be the better model. And there are some reasons why this would be a really nice model, because it's linear in diameter and H, whereas the model up here is not. Now, but I may also find that, well, actually, you could think of d squared h sort of like an interaction term that's mentioned in the text and that sort of thing. Well, yeah, so we could have a b1d plus a b2h plus b3 times the interaction term is that, you know, a tall skinny tree may be very, very different than a short wide tree as far as its overall shape and so forth. And so maybe there has to be this interaction between diameter and height and then plus alpha. You know, that may very well be the case. And so it's not, even though this is a cylinder and this one down here is that nice linear case, it's not at all obvious, certainly of these three, what the best model is. And it could be that, you know, I want some combination of these things. I may want it to all be about height, or possibly about diameter, you know. So well, let's go with diameter, since I gave you diameter and diameter squared. I didn't give height squared. Maybe I should have, but you know, here's a polynomial plus our alpha, and it's possible that because of given shapes that it may have so much more to do with the diameter, and it may be a diameter plus a diameter squared kind of terms. That's a polynomial. Maybe this is the best thing to use. And so in this project 6, what we're trying to determine is which one of these, you know, I've mentioned 4 different models. There are other combinations I could use. I could put everything together that I have in there. So I could have that volume is some beta 1 times diameter plus beta 2 diameter squared plus beta 3 times height plus beta 4 times diameter times height, that interaction term, and plus beta 5 diameter squared times height, and then plus, I'm running out of room there, my alpha, my intercept. So that could be the best predicting model and so forth. And so what we want to do is go through looking at both our p-values for the coefficients and at our adjusted R squared as we look at these, and also just thinking about what we might want, you know. So again, the height of a tree is really hard to measure, and so again, I might really hope that maybe this model, this polynomial in diameter, would be good, because then I can measure the diameter of a tree pretty easily. but getting its height is not so easy. And you know, and of course height, it's not, you mean height to the top of the crown, you know, the very tip top of the tree, or is it a height to like where the trunk begins to split or something like that? You know, height can be a very difficult thing, but the, you know, diameter pretty easy. I can do that. So I would really love a model that was just this diameter and diameter squared, or even simpler if it just had to do with diameter. If that's a good enough model, well, I'm very happy with that. You know, again, I kind of like this model up here with the d squared h, because it looks a lot like r squared h in the volume of a cylinder. But there again, well, now, you know, I have to multiply those columns together and so forth, and maybe I don't want to. And, you know, and it can be, it's not so much me, but it can be that, you know, I'm going to send out 100 workers in the field, and I want to make sure everybody's doing the same thing and so forth. And the simpler it is, if nobody has to multiply anything or something like that, well, that's easier. Or again, if nobody has to find the height of the tree, much easier. So, you know, it's just because, say, a cylinder is more like this one up here, or just because the second one is a very stereotypical linear regression in the sense of, well, with more than one variable, more than one explanatory variable, you know, neither one of those may be the best answer. We may get a better fit. And again, why? Well, because trees probably aren't that linear. But on the other hand, they aren't exactly cylinders. So maybe one of these other models works better. And so that's what we want you to kind of go through and talk about and discuss. I've limited it in that you can only come up with so many different models. And I'm not really asking you to try each and every possible combination of those columns, but I'm asking you to try a few, and then to look at that adjusted r squared. And I'll have another video where I'm kind of talking about some of this using the spreadsheet. But that's this idea of Project 6, is we're really just trying to decide among some various models. And so we'll call it good for this video.